So our next speaker for today's evening is Professor Yang Chen. He's a professor of physics and astronomy and a professor of electrical and computer engineering at Purdue University. And he leads an interdisciplinary research group that works on quantum matter and devices involving systems such as graphene and 2D materials, topological insulators, and cold atoms and molecules, and explores their applications in electronics, sensors, energy, and quantum information. Professor Chen received his MSc degree in mathematics from MIT and a PhD in electrical engineering from Princeton. And then he was a postdoc in physics and nanotechnology at Rice University. He's also a fellow of the APS. So I set the stage open for Professor Chen to talk about Atomtronic Spintronics.
Okay, thank you very much for the kind of introduction. I hope you can all hear me okay, all right?
Yes.
So it's a great pleasure, and thank you for the invitation in this wonderful summer school. So I would like to, let me see, advance the slides. Okay, so again, very much thanks to the organizer and colleagues, Kolkata, India. This was my last trip, actually, the only trip to India.
So, Professor Chen, sorry to interrupt you. Are you comfortable taking questions in the middle?
Of course, feel free.
Okay, that's great. Thank you.
Maybe where I think
sure.
you know where this is, and
okay.
hopefully soon we will be able to do this kind of in-person meeting in near future, and I'll get best wishes to all of you guys. But it's also wonderful we can have this online meeting. I think future meeting may very well be hybrid, that we can have speakers from all the time zones and all the world. So thank you again. So here is my kind of plan. I like to discuss a few general ideas. Actually, I think for most of the time, probably if I focus on the first idea, which because it probably is discussed a little bit less than some of the other topics that you may have heard more often. The idea is basically a new approach to control chemical reaction. I will mention that there's a big field using laser to steer chemical reaction. Usually you work on the laser field, pulse sequence, or multiple colors and so forth. But a new approach we hope to develop, and I will show you the experiment results that is a demonstration of this, is to actually, instead of working on the laser fields, but you're actually preparing your reactant or atoms in some kind of quantum superposition states, which actually allow these atoms to react in multiple pathways, sort of like a Young's double slit, could be a multiple slit process in the chemical space or generic Hilbert space. So we now call this quantum chemistry interferometer. I hope this is a general new approach to control chemical reaction, okay, that I think you can try in many systems if you have ability to prepare reactants in quantum superposition. And in our particular case, we demonstrate in photo association of rubidium atoms in the BEC, but I think this should be a more general idea. And also, if time allows, I will discuss perhaps more briefly two other ideas. So the first idea is more about two-body physics, kind of chemistry or molecules formation. And then the two other ideas are more related to perhaps condensed matter physics flavor or quantum simulation, if you want. That has something to do with the synthetic fields, for example, synthetic electrical magnetic fields for charged neutral atom. So normally, these electromagnetic fields is for charged particles. Here, by manipulating laser beams, you can generate synthetic gauge fields to act on even neutral atoms, which allow you to study quantum transport, for example, in some analog with the solid state physics, but there's a lot of new things here. You can also make these fields spin dependent. If it's a spin dependent magnetic fields, that would be a synthetic spin orbit coupling. If it's spin electric field, which is what we demonstrated in this work, it would be actually you generate spin current. You actually generate what you can call a condensate or spin condensate collider. And turns out this may look like two-body physics, but really a lot of many-body physics. Okay. And probably I won't have time to go much into this, but I'll just briefly mention the synthetic dimension or synthetic space that you can generate to realize many novel synthetic geometry or topology, even systems cannot be easily realized in solid state materials, such as a emergent crystal, even without applying external ladder, for example, optical ladders. It may be a one-body physics, but it's an interesting kind of a single particle physics, allow you to study object in synthetic space. If I don't get much time to talk about this, you can read more about this in these references. And of course, I want to mention there are postdoc openings in my lab right now to study any of these subjects for those students interested. Welcome to contact me. Okay. I already mentioned, actually, all of these ideas are pretty general. In fact, it's all really fun if you're a student or young researchers think about some future things might be interesting to do. It would actually fun to explore realization of these type of situations in novel systems and setups. But in our case, we'll be studying these implementation of these ideas in a particular platform, which I think is a very powerful platform. That is a spinner or spin order called BEC. In our case, rubidium BEC. But these ideas are more general beyond that. Okay. So a very brief, you probably have seen version of this, review of our experiment setup, which is, as mentioned, is a rubidium BEC at Purdue University. Of course, one thing you may have realized from the introduction, I have a background or even primary background in sort of the condensed matter physics, studying also a lot of materials. But the one thing I really like about these CODAS system is that it's both AMO system, but it's really a condensed matter system, quantum matter. It's wonderful because it allows you to slow down and blow up quantum phenomena to very slow time scale or bigger length scale compared to typical condensed matter systems. So you can take photos, take videos of these things. For example, on the left, it's just a Stern-Glock experiment running in modern days. You separate different spin components of the condensate in the magnetic field gradient. You can see this process. By the way, our setup is a so-called optical BEC. At the time, it was the first BEC in Indiana, but now I think there are many of these things perhaps in Purdue, in IU, so on and so forth. It's all based on pretty standard technologies now. You know, many Nobel Prize winning important techniques in AMO physics, laser cooling, trapping, so on and so forth. There's a little bit small technical difference and maybe improvement in our setup for those people who are interested. This is in the 1550 so-called telecom laser optical trap, which actually it's a laser we happen to have, a powerful laser at the moment for some other purpose, but it produced some complications, but we're able to solve this complication due to some of the shift in the excited state by optimizing evap cooling in this kind of optical trap. The codes are, some people find these codes to evap cooling useful. So I just mentioned this is the work of from PhD student Abraham Olsen to optimize evap cooling of any atoms in optical trap. Interesting. Okay. One thing I want to draw attention is, which is also example of the kind of control we have in these cold atom system, is that we can couple to their internal states. We call these spin states, which is powerful, obviously, a knob we have. You can, I think these animation will work. So you're seeing, hopefully, the Rabi oscillation in these movies oscillate between different MF or spin states over the condensate, driven by RF coupling. You can also grab this by Raman coupling. You see also, this is an example of BEC matter wave diffracting from a transient optical grating, basically optical lattice. If I don't tell you this, this is interesting. Also look like something on the grid. It's just like laser can diffract from matter grating, like in your laser lab, matter can diffract from optical grating. So this is also interesting. And this grid-like structure, again, it looks like lattice. This is a powerful idea. When you have these kind of discrete spots you're seeing here, you can treat them as sites in the synthetic dimension, which is a powerful idea. Maybe we'll briefly mention, but it's a powerful idea at the top. Okay, it's a powerful idea that you can take in many other situations. All right, so next, let me also make a digression. It's particularly wonderful to mention this in the summer school organized here in India, because Raman is one of the, obviously, the most important Indian scientists with tremendous contribution to science. Today, the Raman spectroscopy, obviously, is an elastic scattering process that you can use to understand obtain fingerprint of molecules, nanomaterial solids. And today, perhaps the majority application of this kind of Raman scattering or spectroscopy is an incoherent Raman process. You have some underlying levels. You can exchange energies with the incoming photons. You can shift up or shift down. You measure that energy shift. This is Raman scattering. And just as an example, as I mentioned, as was mentioned, we also perform studies on nanomaterials such as graphene. There's one of the earlier Raman scattering of a twisted bilayer graphene, which is a different big topic today in kinematic physics. You can see these kind of a breathing mode between the two graphene sheets, kind of almost like vibration between two atoms, but here each atom is a super atom, is actually a sheet of graphene sheet. And other modes, vibration modes, which shift your light up frequency up or down, which is Raman spectroscopy. So these are very standard diagnostic tools in pure research these days, but these are all incoherent Raman process. Okay, the Raman process that I'm going to talk about, which is a very important addition to our BEC setup, is a coherent Raman process, which is really you can call it optical dressing. Okay, so this is an important aspect of light matter interaction. At a very fundamental level, the light matter interaction can be thought of. Let's imagine you have a two-level system, labeled up and down. In this case, it would be some levels of the atom. If you have some kind of coupling between them two, whether it's RF or Raman, in the case Raman, you put a coupling intensity, some kind of a radio frequency, whatever, on the off-diagonal element of this 2x2 matrix. By the way, the 2x2 or 3x3 or 4x4 matrix, these are the level of quantum mechanics we'll be doing in this talk, but it's a very fruitful way, simple but very fruitful way to do quantum mechanics and quantum science, of course. And in addition, the atom have if you don't do anything, has the free particle dispersion, okay? So you can put the dispersion here. And because this is a counter-propagating Raman process, the coupling involving absorb and emission of photons with opposite momentum, so it actually involving a momentum transfer of 2 units of the recoil momentum Ki. So it reflects that fact by saying it couples a momentum with a P plus Kr and another momentum P minus Kr. Okay? This immediately is very interesting because here are my free particle dispersion, which I already shifted them by 2 units of recoil to prepare this coupling. Once you turn on this coupling, it opens a void crossing or gap between this dispersion. I also have labeled these two uncoupled curves by their corresponding spin states, up or down, or red or blue. It can be any two discrete quantum numbers. And then once you couple them, the ground state or ground band, you generate something, a new dispersion, so to speak. It's no longer the free particle dispersion. It has this interesting double minimum. If you reverse this label, which we call quasi-momentum, you reverse the spin states to generate something. People call this synthetic spin over the coupling or synthetic band structure, or spin helical, in the sense you reverse the spin, you reverse momentum, you reverse the spin. But it's more, even further, each of the new eigenstates is really superposition of the previous uncoupled eigenstate, which is labeled by its spin and momentum. And now it's kind of a superposition of both spin down and spin up, and with the momentum different by 2 units recoil. Okay, and you probably also notice this structure where spin is tied to the momentum looks like kind of like an EPR. Of course, this is in the one particle, but people do call this spin momentum entanglement. Okay, there's some interesting aspect of this discussed in this paper. We wrote with this nice theoretical chemist discussing some aspect of this entanglement. This is basically set up. So we have a BEC going to be, or atoms loaded or subject to this kind of spin momentum coupling induced by Raman optical coupling. Okay, but in the simplest case, you can understand them in this 2x2 matrix. Okay, all right. But you can generalize to 3x3, 4x4, even n by n. So this is a really rich trick you can use. All right. Just a few more words. This is, of course, a very, this is a pretty active field of research in AMO physics. In this particular scheme using Raman, first demonstrated at the NIST experiment group and now used in many labs. For example, in the case of rubidium, you can couple, of course, multiple levels. Typically, we work with the F1, but you don't have to limit to this. But we typically work with F1. There's 3 states in F1: ground state rubidium, right? Given the rubidium quantum numbers. In the simplest case, you can, of course, there's 3 levels, but for example, there's a if you use a little bit, magnetic field, there will be a quadratic Zeeman shift or difference between the Zeeman split between these levels. So you can, for some situations, you can ignore a 3rd level to limit the coupling in just 2 of the 3 Zeeman sublevels of the ground state, because they're splitting Zeeman split a little bit different. But you can couple to multiple levels. And I already mentioned the idea of rewrite this in a 2x2 matrix. There's another important trick, at least conceptually, but it's give you a new insight that's important. When you have a 2x2 matrix, you can rewrite this thing in terms of Pauli matrices. Okay, so look here, and you can see the off diagonal, which is your Raman coupling, laser strength. Again, it doesn't have to be Raman. This can be ARF coupling, NF coupling. So this acts when you write in the this Pauli matrix, it's this coupling times a sigma x. Recall what sigma x is. So this Raman coupling looks like fictitious magnetic field. Okay, this is one way to generate a fictitious magnetic field just using these coupling. But also because now we're doing the Raman coupling particularly, so they have this momentum shift in this diagonal part. If you expand it, you realize you get a p times k, but also the sigma z. There's a plus sign, there's a minus sign here. This is sigma z. So this kind of Raman coupling gives rise a fictitious momentum times spin. So this is the spin momentum coupling. So you can simulate this kind of a well-known Hamiltonian, which people, for example, study in MAR or study in Spintronics. So that's my work, Atomtronic, Spintronics. Using not necessarily real magnetic fields, but using these fictitious fields, which you can provide laser beams, for example. So this is very powerful. I also draw analog, but also contrast. I mentioned you generate some kind of synthetic band structure, quasi-momentum. Of course, you're familiar with how the band structure emerge in the crystal lattice. Of course, you can do this by optical lattice or periodic potential. Then you're coupling different Fourier waves or plane waves that differing by reciprocal lattice vector, which is Fourier component for periodic potential. This is how band structure generates. You can also understand in this very simple coupling. Of course, you do this for all these different shifts of the integer units of the reciprocal lattice vector, and you generate this periodic band structure. Okay. Of course, at the end of the talk, I mentioned you a trick. You can generate band structure or periodic band structure even without optical lattice through this kind of Raman coupling, which is also fun. But here in this level, it's even much simpler than this kind of band structure generated by periodic potential. You at the minimal level, it's just two branches to couple. Therefore, there's no periodic structure yet here. But you do have this concept of the quasi momentum and eigenstates, the superposition of these different plane wave basis states. So this is even simpler than the periodic band structure. Okay, so let me go ahead to talk about this first idea. Okay, so I introduced our experiment setup, which is a DC, but subject to this kind of optical Raman dressing or coupling, okay, spin moment coupling. In the end, for this first part, just spin part is most important. So I mentioned this first idea is we hope a new way to study chemical reaction, that when you can prepare the reacting atoms or reactants in some quantum superposition states. In this case, we'll be prepare them or dress them into the superposition between different MF spin states. Then they can undergo chemical reaction in multiple pathways involving combinations of these different spin states, for example. Then you can have an interference between these different pathways and control them using your laser fields, or the way you prepare this quantum superposition. Okay, so we call this, not call this chemical interferometer. Let me make a very general remark that, of course, it's a very long-standing dream in quantum chemistry, or in chemistry in general, where we can using laser beam to steer or control the reaction to selectively breaking the bonds, or changing the configuration, so on and so forth. This is, of course, is a huge field. People have been studying for several decades. Nice textbooks on this you can read more about. In general, okay, there are two classes of techniques that is, I mean, I should say this dream has not been fully realized. So this is still a frontier. It's not so easy to actually really steer these chemical reaction using laser beam in well control. Of course, there's tremendous amount of progress, but this is still a dream in many aspects. There's still many things need to be completed. But in this, what I call coherent photochemistry, obviously in laser involved photochemistry, either directly do this or participating mechanism. But typically, one of these two domain or regions or classes of approaches, one is to try to design many pulses or try to do pulse engineering of a laser to steer the chemical reaction. Or you can apply multiple colors, maybe some of different laser fields to sort of some interference between these different optical fields driven reactions. Even in the pulse engineering approach, fundamentally, it's you can also understand in terms of some of these interference processes. I should mention all of these very fruitful and well actively studied approaches focus on using engineer the laser fields that steer these chemical reactions, whether using pulse engineering or multiple photon or multiple color approach. The approach we are doing here is in some sense much simpler at least in terms of laser fields. You don't need complete laser fields. You just need one photo station CW laser field in the simplest case. But instead, you actually instead of controlling the laser fields, you control the starting reactant, control their quantum states, which is what these cold atoms, I should say, these are laser chemistry, of course, people studying things much beyond cold atoms, ranging from reactors in atmosphere molecules to astrophysical setting to biomolecules. But the nice thing about cold atoms is that we can have very precise control of the quantum state. You can do this quantum state by state chemical reaction, which is really cool. And by controlling the reactant quantum state, particularly the superposition, you can actually control these photochemistry using very simple laser fields. So that's we hope this is another general approach that can be applied to many settings. Also, brief review on the photo association in the summer school. Perhaps you have heard several times already this, but I like to mention, of course, this is our photochemical reaction. Using a laser to kind of glue two colliding atoms into a molecule. The first time you heard that maybe it's a little surprising, laser should breaking things apart or evaporate things, while they actually glue things together. Of course, you're gluing them together in a higher energy potential level in the electronic excited molecule. So these are the potential, of the molecules. You're forming this excited molecule, which can decay either to a ground state molecule, which is very interesting. I won't go much into that, or most time they decay back to atoms, which may not be trapped in your trap, so you can measure this as a loss. This is a particularly fruit subfield in cold atom. Particularly, people have made almost all the this is physicists' favorite molecule. Maybe chemists thought this would be too simple, but for physicists, this wonderful molecule, the bi-alkali molecule, either X2, a homonuclear, or XY between two different alkali, because you can control them so well. There are a lot of reviews. You can read about this. We had found some years back. This is actually the wonderful work by our co-organizer, Professor Dutta, in his thesis work at Purdue. It's a wonderful thesis because when I went to grad school, they say a good PhD thesis should be something when you are end of or finish thesis, you become the world expert in the world, knowing most about this topic, even more than your PhD advisor, which is certainly the case with Sourav. He is the expert in lithium-rubidium cold molecule and photo association. In fact, he made the first cold lithium-rubidium molecule, with one of the last alkali molecule to be made, and many nice spectroscopy work. This is almost like theory curves, but looking at these laser spectra, you can read these kind of nodes in the wave function in different vibration levels just from these laser spectrum, which is very nice to see. But Sourav demonstrated very nice photo association of lithium and rubidium, even close to unitarity, something nice about the system. So we learned quite a bit through this kind of work, also in collaboration with a colleague Dan Elliott at Purdue Engineering Department to play with these this kind of laser chemistry. Although for this I'm going to apply this photo association in just rubidium alone. So we're making rubidium 2 in the Bose-Carbon state. So that's the setup. So just a bit more reminder. So the particular scheme we're applying these this is a CW laser, one photon transition. We apply slightly red detune from atomic resonance. Okay? In reality, you'll be detune these, for example, many tens of gigahertz or even more, and search in a range to see if you see a resonance. What do I mean by photo association resonance? So this is example. So you monitor the number of atoms. In our case, we'll be taking pictures of condensate. Okay, this is EC, which and if your laser hits a special frequency, so this is already measured tuning from a known photo association resonance. You hit special frequency, you see a loss of atoms. This is because the atoms, as I mentioned, are forming these electronic excited molecules, and most of them decay into free atoms. They no longer trap. So we see these resonance. In reality, of course, you can have lots of resonance. You pick one particular line, that's one photo association line. Okay. And in the case of the BEC, okay, they are well-defined theories, pretty well-developed theories to understand. You have to consider the density distribution BEC to really properly quantitatively model these photosynthesis process. But that framework has been developed. So we would obtain the calculate a number of loss or fractional loss, which is related to a important dimensionless parameter, which is eta, which relates to the the photosynthesis rate constant. Photosynthesis is two-body process, so the reduction of the density or number of atoms is related to the square of that density. So it's a two-body process. You need two atoms to collide. It's a negative, it's a loss process. Right? But from these loss you measure, you can extract this photosynthesis rate constant, assuming that you know the other parameter density is the loss length of a laser, photosynthesis laser, so on and so forth. Okay. So it's a reasonably well-defined procedure. Okay. I should most briefly mention, I won't go into this. It's actually photosynthesis is a powerful tool. So my little short sentence is you can use chemistry to study physics. What I mean is by watching how a quantum gas or even quantum many-body systems such as correlated quantum gas or states you can form in these species, watch how they react. For example, photosynthesis, you actually learn a lot about the very interesting physics underneath. For example, one physics you can learn, which I think a lot more need to be done, is to you can use these kind of photosynthesis rate to actually measure what's known as contact in quantum gas. But I won't go back. Your work in this talk the same. Okay. Okay, so I mentioned you can have fun all day long, measure lots of photosynthesis resonances. In the case of spinner rubidium BEC, a lot of the previous work has been done by Michael Chapman group in Georgia Tech that told us the position of all these photosynthesis resonances. Most of our work, we pick just one. Okay? So we're not so much in this part of the talk, not so much in the molecular physics or spectroscopy aspect, but mainly interested in how we can use this to do something interesting in this post-condensate ability. We can prepare atom in this quantum superposition. And the particular photosynthesis line we picked is what's known as a spin-sensitive photoassociation line. And on a simple level, you can just understand this photosynthesis transition has a particular selection rule, which is very simple, which makes our life even easier. Is that it required the sum of the MF quantum number of two colliding rubidium atoms to be 0. So because we're dealing with F1, there are only 3 possible MF levels, 0 or plus minus 1. That means it can only react to atoms that are both in the MF 0 state or react to atoms in plus 1 or minus 1. Here's the evidence from the previous work. If you again a loss, a dip means you have made molecules. Okay, so if you prepare the atoms or in this case, or the condensate atomic concept, or in the if you have a simultaneous +1 or -1, then you get a nice reaction. If you only have so both epsilon and theta are one of the examples of these spin sensitive line. That's just like epsilon. If you prepare a mixture of -1 and 0, only 0 component can react. The -1 has no reaction, so you do not see any loss. There's no reaction between -1 and -1, not allowed. There's no reaction between -1 and 0, also not allowed. Okay, so this is a nice demonstration of this system photo association. So that's our starting point. What do we go beyond to this is to say, now we have this ability because we have this spin, we have this Raman coupling, for example. It gives us ability to dress the atoms or the reactants into these superposition between 3 different MF levels. Okay. Now, if we apply this spin sensitive photo association to atoms that are addressed in this superposition state, what happens? Okay. The fact that we use this spin selective transition photo association line simplify things, but the physics is more general. You can use more general photo association line, but then you just have to consider a lot of other reaction pathways. But because we chose this particular simple one, which had only these 2 reaction channels, it simplified our experiment and analysis. So a little bit more on the detail. In reality, I said we are coupling using Raman coupling to address these 3 MF levels in rubidium. So you have to write as 3 by 3 matrices. The general idea is the same. So you put this Raman coupling on the off diagonal. And once you do that, resolve this eigenstate, you get this again synthetic band structural eigenstates or eigenenergies labeled by this quasi-momentum, which in general are the superposition, the states of the 3 different spin states with a different momentum. Even though the fact we use the Raman coupling to produce these superposition states, which are superposition of both different spin states, MF, and both momentum. For this purpose of this part of the talk, where we focus on the chemical reaction induced by photosynthesis, the momentum part is not too important. Okay. Mainly it's a spin superposition that is driving the physics we observe. The reason the momentum part is not too important is based on this very simple length scale argument. Because we are creating these momentum couple are on the order of the recoil momentum of light. So photon wavelength is roughly on the order of 100, let's say micron. So it's on the order of micron length scale. But the photo association occurs at the length scale of tens of A0, which is a few nanometer or tens of nanometer, which is much shorter than this micron length scale. Okay. So to the first approximation, we can ignore this momentum part for this photo association physics, because from any other physics, for example, data I've discussed in the later part briefly, the condensed matter style physics, we do worry about physics on the length scale of the micron. So it depends on the length scale of physics you're studying. Okay. How do we know we created a spin? But however, this momentum part do give us a nice kind of at least visualization, because if you don't couple them, you're dealing with these mixtures of condensate in different MF states. But we do couple them. If we manage to put them in a superposition state, they will differ by have different spin state would have different momentum. I talk about the spin momentum entanglement, meaning once you know the spin, you know the momentum. And you can measure those or image momentum in our, these imaging, because they basically show up after time flow, some offset in the position of these the atom cloud. So this is a nice way you can read. If you're totally confused, at least you can read which spin state they are based on where they show up. And also when you see this kind of this diagonal pictures, we're dealing with a spin. Within a superposition, a BEC prepared in a superposition between 3 different spin and momentum states. So it's a nice visualization, at least. Okay, so I mentioned we monitor these photosynthesis by comparing when the photosynthesis is off resonant versus when it's resonant. Okay. When you turn on photosynthesis or make resonant, you induce loss. In this case, obviously you see a loss. That's particularly obvious in the spin 0 component, less obvious in the spin ±1, just because in this case there's still some loss, but here spin 0 is more dense. Okay? But when you prepare a superposition, even though the population is generally comparable, their loss in this different component are all similar. So this is summarized in this plot, shows a normalized atom number or loss for different spin components. So in a statistic mixture where there is no particular relation between these different spin components, they undergo photosynthesis pretty much independently. Okay, in this case, actually very weak in the ±1 channel. But when you prepare it into a superposition, they all undergo reaction at the same rate. So now this is itself is actually a demonstration. You are dealing with this is not 3 condensate. Okay, so this is 1 condensate that is prepared in the superposition of 3 different spin states, and this is one of the demonstration. They are all one thing. So they all under loss under in the same rate. Okay, of course you project them after time flight into their 3 state basis, but this is 1 condensate. This is 3 condensates, but this is 1 condensate. Okay. All right. But perhaps even more interestingly, for the purpose of this talk, is to see what happens to this photoassociation, what happened to this loss once we dress these atoms into this superposition. But we also have a control of this superposition coefficient, and these are controlled by basically the coupling strength of the Raman laser intensity that we apply. Okay, again, I probably should have mentioned this, but when you these are eigenstates, of course, of these 2x2 or 3x3 matrix. The coefficients, right, the eigenstates, new eigenstates are the superposition of these uncoupled eigenstates, and these coefficients are fully controlled by this orthogonal coupling parameter, in this case, just the Raman laser intensity. And so we can measure these photosynthesis molecular resonance. Again, loss means we're making molecules for successive increasing amount of strengths of Raman coupling. So we are increasingly dressing them into the superposition states. Okay? So if there's no coupling, we're measuring a bare, in this case, a bare spin 0 condensate, okay? No superposition. But if we turn on coupling, we are making superpositions, and these coefficients are tuned by this coupling parameter. Note, because these coupling are introduced by Raman laser, the Raman laser itself would have some small effect on the, say, positions of the VC, so on and so forth. So to compensate for that other effect, we do an important control experiment. We do turn on this Raman coupling, but we turn on with a very large 2-photon detuning. So if you have very large 2-photon detuning, again, then you are actually not going to create these superpositions. So even though you can turn on these Raman beams, if they are far detuned, you actually don't create these, you don't dress them also. So let's see what happens. All right. So with a no coupling, we're dealing with a bare spin 0 DC, nice reaction on the go 0-0 channel. A little bit of coupling, I guess, is still pretty happy. And when we start to turn on more Raman coupling, meaning we address the atom into these superposition state, you see again, if there's no detuning, we are properly dressing them into this spin superposition states. There's actually less loss or less chemical reaction occur. If you have far detuned, even though you turn on Raman beam, as long as you're not making superpositions, you still have this nice chemical reaction. If you turn on a lot of coupling, okay, which means you fully dress them into these superposition states, then this reaction is actually suppressed completely. There's no, we're no longer making molecules, even though the 0-0 condensate or ±1 should be making molecules, but we're not. But if you're far detuned, meaning you're still only preparing a spin 0 condensate, you're not making superpositions. Again, you still can make chemical reactions. So by dressing them into this superposition using this coupling, you can completely turn off this chemical reaction. This is very interesting. So what happens? So this can be understood by this, the quantum chemistry interferometer, or interference between 2 reaction channels that I mentioned at the beginning. So recall, on the very general grounds, right, we're talking about some kind of transition. So this photo association, again, 2 atoms collide. So this is a general some kind of scattering, right, or transition 2 atoms between the molecule. is related to the wave function overlap of matrix element between the scattering state of two atoms and the particular molecule wave function you have into the operator. And this is rate, this is square of this matrix element. And if you think more carefully, actually most of these are not important. These are generic, but these are, you can lump most of these into some unimportant detail. The most important thing is this scattering wave function, in particular the spin part of scattering wave function. The moment part, again, I say you can ignore for this type of photosynthesis transition. The spin part of wave function is what's interesting and novel in this, because you have prepared now each atom is not in a single spin state. It's simultaneous in 3 different spin states in a superposition. So the spin part wave function is a superposition. So when you do a scattering, 2 atoms, the joint wave function, joint spin wave function one is a product or whatever, tensor product. It's at least 2 joint spin. So you can write in this tensor product. So generally, you have 9 elements out of this. But fortunately, I said we select a very simple photo association that we only need to worry about 0-0 combination and plus and minus 1. We can throw away AA combinations. Another very important piece of physics, which is well known to the students that are taking quantum physics, which is everybody, is this Stern-Glock coefficient, where you combine two angular momentum, right, in quantum mechanically. And you realize this F is 1. We're dealing with F1 state of rubidium. MF can be 0. So this is how to sum 2 spin 1 particles. The 0-0 and plus minus 1, they both contribute to either total F2 or total F0 in this or 1. But in this case, turns out is the 0-0, the total F0 channel that is important. So this is a knowledge from the previous spectroscopy work, is that this particular photostation we pick act on the total F0 channel. But what is interesting, so that's actually a reason why only 0-0 and plus minus 1 contribute. But what is very interesting is that they contribute in the opposite sign, because the Stern-Glock coefficient in front of that total angular momentum is actually opposite sign between these 2 channels. So this opposite sign gives us a destructive interference between these 2 channels that they can simultaneously react. Without a lot of details are in the proportional factor in front of this. But most important thing is that this rate should be proportional to the square, being a rate of this combination, which is 2 times coefficient C minus 1, C plus 1, or 2 is from the bosonic symmetry, because plus 1 minus 1 is the same as minus 1 plus 1. Minus signs because it's opposite Stern-Glock coefficient, so minus C0 squared. Again, either it's a C0 squared or C plus minus 1, show this is a 2-body process that you're reacting 2 atoms. If you expand this, you realize these rate will be some kind of background rate, which is if you only react 0-0, you prepare atoms only in 0-0 state, this is background rate. But if you prepare in this kind of superposition, the rate should be controlled by the superposition coefficient. Again, minus sign, and this term, cross term is from this interference between these 2 channels. Now, as I mentioned, when you actually turn on, increase the strength of Raman coupling to actually start to dress them into the superposition states, you gradually turn off this chemical reaction, suppress the rate to 0, which you can only explain if you consider this quantum interference effect and this cross term. Otherwise, you just cannot explain this almost complete suppression chemical reaction. What happens at the large Raman coupling, if you solve your 3x3 matrix, you realize the superposition coefficient is such that the spin 0 coefficient is 1 over square root 2, a spin plus minus 1 coefficient is 1/2. Okay? So you are making more atoms in the 0 and a little bit less in plus 1. But this coefficient is nice because if you plug in these 2 times 1/2 minus square root 1/2 square, you get 1/2 minus 1, 0. So that's why we get completely suppression, because it's destroy interference with minus sign. Okay. You can also do another interesting control experiment. You can keep the Raman coupling on, so you are dealing with a superposition state. Now you tune these superposition coefficients by tuning the proof of the detuning. What happens if the detuning is large enough? you tilt the superposition back to the either purely -1 or purely +1, as I said, +1 -1 itself not going to react because they don't satisfy the sum rule. The sum -1 plus -1 is -2. +1 plus +2, they are not zero, so the reaction is not allowed in this spin sensitive photossensation. Only near the zero detune you get a strong reaction rate. Again, you have to understand, if you want to understand this quantitatively, you have to take into account this interference term. Okay.
Professor Chen,
Yes.
I think we have another 3 minutes for you.
Yes.
So would it be possible for you
sure.
to conclude in 3 minutes?
Yes, it's indeed. This is conclusive of this part.
Okay.
So this is approach that we by dressing the atom into superposition, you can take advantage of the interference between different reaction pathways. In this case, 0, 0 and ±1. In this case, destructive interference will turn off camera reaction. Okay, but this is a general, pretty general thing, and you can do try to apply this to any other type of a scattering or reaction process, as long as you have ability to prepare reactant in some quantum superposition state. It will be really fun to see how this play out in these other settings. Even within the rubidium system, we see there are a lot of work we are hope to explore, we can explore in the near future to realize construct interference, therefore full control. Instead of using the Raman, you can do RF dressing to create a superposition state to different F states, which have different CG coefficient, may allow you to realize construct interference. It's particularly interesting to use actually spin insensitive photossensation line, which you have lots of reaction channels. And we believe if you prepare the coefficient correctly or superposition correctly, you can actually observe some kind of a super radiance like we heard about Dickey idea in the last talk, big enhancement due to simultaneous into lots of channels that's construct interference with each other. And also in the future, it's very interesting to study PA in these kind of many body system to probe many body physics. And this is just a very recent progress. You can read more about that. Using RF coupling, you can actually indeed switch the sign, so to speak, with some of these coefficients actually preserve a both constructive and destructive interference of these photo association. So I think I will stop here. So I mentioned that probably you can only mainly focus on one idea, is this idea of preparing atom in the superposition. You can actually open up ability for them to react in many channels and control the interference between reactions. You can read more about the other ideas that I think are interesting. One, people can explore in these spin orbit coupled EC systems by treating these spin degree freedom as a synthetic dimension or synthetic or coupled to momentum. You have the synthetic magnetic fields. You can generate spin current or collision between condensate. You can read more about it in these papers. You can realize a emergent density wave or crystalline order just by playing with these Raman. Another momentum part is important. You can generate a synthetic reciprocal lattice vector, so to speak. You generate a synthetic band structure, which you can read more about in this reference. So I think my time is up, so I'll stop here. I hope I have time to ask some questions if there are any.
Okay, so that was a wonderful exposition on photo association and spin physics. So I think we'll probably have time for one question if anybody wants to ask.
Hello.
Yeah.
Sir, I have a very naive question. I don't know because I have came in mind that can you observe this chemical reaction type behavior in photosynthesis process? Means there is a photon absorbed by the molecules of skin of the leaf. Actually, I don't know is it possible or not.
Okay, thank you for your question. I think it's a great question. It would be wonderful. People, I assume when you say photosynthesis, you refer to, for example, the life, right? The plants, those things you can have a photosynthesis. Well, let me just say two things. One, it's very interesting. People indeed are exploring the quantum effects. I mean, there's still ongoing research how much quantum coherence there is to these photosynthesis process, electron transport, so on and so forth. So I think this is a very interesting direction to think about. One of the challenge, of course, when we're dealing with these big molecule, large molecule, that first of all, it's at room temperature, and the quantum coherence generally weak, short-lived. But I'm not saying there's none. So the good thing is to study these cold atoms and molecules is more controlled. You have a better way, better control in the state. But I definitely think there is a possibility. I don't see anything preventing some effect like this from happening in the more complicated molecules and reactions. As long as maybe you have to have a much shorter window of time scale to explore this. But I think it's certainly interesting to think about how you can prepare, because now one of the most important tools we have, we can prepare things or even more complex things in some kind of quantum state or even quantum superposition. As long as you can have that ability, one should explore whether these interference in the Hilbert space can be taken advantage of to control their behavior or their reaction.
Okay, I think we are almost out of time. So thank you, Professor Chen, once again. And it was a very good overview of your work, and we are very happy to have you here for this session.
Thank you very much. Let me stop sharing.